A very good afternoon to all of you. I am Ehla welcoming you all on behalf of eMobility Plus and the First U Group to our webinar on driving innovation in EV battery design with multiphysics simulation tools. I take the pleasure to thank our partner COMSOL for their immense support to organize this webinar. Please allow me to introduce our session expert, Dr. Rustam Singh Shekhar, the Applications Manager from COMSOL Multiphysics Private Limited. Dr. Rustam Shekhar is specializing in electrochemistry and battery simulation. He received his PhD in Energy Science and Engineering from IIT Bombay, Master in Chemical Engineering from IIT Hyderabad, and Bachelor's in Chemical Engineering from MITS Gwalior. His expertise includes electrode microstructure and cell and pack level modeling. Before we dive into the presentation, let me give you a quick overview of what to expect from today's webinar. As we know, in automotive design, modeling and simulation has become an important tool in the study of the design and operation of battery systems. The COMSOL software and its add-on battery design module provide user-friendly yet powerful and versatile capabilities for describing batteries and electrochemical cells. The software also features multiphysics capabilities of coupling the electrochemistry within a battery with structural stress effects due to intercalation, heat generation, heat transfer, and computational fluid dynamics. Multiphysics models can be utilized to investigate thermal management and thermal runaway in individual cells, as well as in battery modules and packs consisting of hundreds of cells. In this live webinar, we will discuss how the COMSOL multiphysics modeling and simulation software can be used in EV battery design. After this, we'll have a Q&A session where you can ask your questions to our expert. But here, I would like to make a small request. Attendees can post their questions in the dedicated Q&A box, and our expert will answer those questions at the end of the session. But before starting the session, we would like to play a small video showcasing what COMSOL has to offer to the automotive industry. I would now like to request my team to please play the video.
Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL Multiphysics gives you the tools to build your own simulation apps. The startup wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted in Developing designs and performing experiments virtually is both cost and time efficient. With COMSOL multiphysics simulation software, you can be sure your results accurately represent the real world. By studying multiple physical effects on one model, no matter the order in which you combine different physics, the software handles them together and solves the mathematical and numerical model equations and provides you with the model results. The entire simulation process takes place in the same software environment. You only need to learn one workflow, no matter the physics involved or the nature of your experiments. Depending on the scenario, you may want to model single physics, one-way multiphysics, or fully coupled multiphysics. The COMSOL software offers all three, and the true advantage of COMSOL multiphysics is the ability to model unlimited multiphysics, where all physics in a model interact, affect each other, and together influence the model results. If you need to add any physics, including your own equations, to your model, you can. The application builder in COMSOL multiphysics gives you the tools to build your own simulation apps. The Startup Wizard and drag and drop functionality help you quickly turn your models into simulation apps with customized user interfaces, restricted inputs and outputs, report generators, and more. This way, you can spread the advantages of simulation to colleagues and customers by compiling your apps as standalone executables via COMSOL compiler, or by making them accessible by web browser via COMSOL server. Understand, predict, innovate, and optimize your processes and designs with COMSOL multiphysics.
Thank you so much, team, for being that with you. May I now welcome our session expert, Dr. Rustam, on the screen. Over to you, sir.
Yep. Thanks, Ella, for wonderful introduction. And as you rightly set the context, that today we are going to talk about battery modeling and specifically about the electro e-mobility. That how what challenges we face generally in the e-mobility sector, and then how that can be tackled by using modeling and specifically in COMSOL. So we will be going through the presentation where we talk about all those burning problems, and then you'll see how those can be tackled by using COMSOL multi scenario. So for that, let me share my screen and we'll begin with our presentation today. Uh, so hope screen is visible to everyone.
Yes,
Okay, thanks. So yeah, today we will be talking about EV battery design, where we want to know that how multiphysics can help you to do the modeling of those batteries, and then once you know the battery, then how can we extend that for the battery pack and then other aspect of it. So when we talk about one battery, it will be just an electrochemical setup where we have charging discharging happening, and then we're having the storing the charge in terms of lithium settling between anode and cathode, or if we be more specific, then negative electrode to the positive electrode. So this simple electrochemical scenario involves different other physics also with that. So let's say if we talk about one electrode, then you just see there will be electrochemical reaction happening on the surface where your electrode and your electrolyte are meeting to each other. But to reach that ion at the reaction site, we may require the mass transport, which will be because of concentration gradient, or it can be because of the potential which you are deploying. So that simple process again, if we go one step ahead, then also we can see one more physics comes in picture, which is your mass transport. Now, that particular process may generate some losses because no process in this world is fully efficient. So then, because of this entropy, you will get some heat generated. Now, if you want to account for that heat generation and the effect of that heat on the battery system, then we will take account of heat also. So this way, this problem grows, and then we will see the problem becomes in multiphysics in nature. So you'll see how that particular problem can be handled. Now, let's just see the entire scenario as in whole. So what we see here, there will be electric vehicle. Electric vehicle, if you want to have the power source with that, so then you will be driving it by batteries or fuel cell. So if you want to drive it with the battery, then you will have battery systems, and then around that, there may be different kind of other setups also will be involved. That will be electric motor, there will be generator, and then internal combustion engine. So if you have a hybrid vehicle, which is current trend in India, where you are getting multiple hybrid vehicles, so those hybrid vehicles will have engines and batteries both at the same time. So now that problem will become more complex because sometimes at some scenario you want to run your vehicle with engine, sometimes you want to run your vehicle with battery, and then when you switch to one power source to other power source, then this powertrain also will change. Based on that requirement, what will happen? Your power demand, your major data for your informations for your battery, which will be your performance side, let's say temperature, or the SOC side, SOH side, or else you can see the thermal and heat generated due to that. So those information will be varying in like a lot. So then, if you will be able to simulate that particular scenario for your requirements, then it will be much better to get one vehicle or a battery pack which can fulfill your requirements and without failing. So there is one more concern which you can face where there will be failures also. So if you can build one set scenario or one setup where you have battery model in detail available with you, you have motor model available in detail with you, and then you can, if you can couple them by using those multiphysics models or the lighter weight models as we saw here in for terms of digital twins, so then that will be more easier to simulate or to analyze the battery and the scenario in this case. So what we see, we have this battery model, and then you can generate the digital twins out of it, where digital twin can be trained by using battery model that can be trained by using your experimental data or measure data or reported data, and there will be some historical data. So then you can combine all of that, and then you can get one realistic battery model which is based on physics, and then the digital twin which is get trained by using this multiphysics model and that background data or the historical data. So now, when you want to model the battery, there can be multiple scales that you want to interested in. So some people may be interested to know how one particular battery is built because they are the battery manufacturer. So then in India, we can see the trend. Now people are going towards the battery modeling or the manufacturing battery by their own. Earlier, the trend was people are getting battery from the other countries, and then they was assembling it, making a battery pack out of it. So these are the different scales and different kind of problems which people face. So when you are a battery manufacturer, you will be accessible to the all material properties with you. In that case, you can make one battery model very easily. But when you don't have that material property available with you, what will happen then? In this case, also you not need to analyze your battery and then want to make a battery pack out of it. So these general problems people face. So let's say now the one more kind of problem which generally in India people may face or engineers may face, because earlier they was working on the engine side, and then the mechanical engineering background person was working on that. Now there's a trend, then those same background people can go and they can work on the battery side as well. So because of this background difference also, where if there is more detailed electrochemical knowledge is required, there will be some problem to model those batteries. So then you can see multiple problems which people may face, and then you want to answer those queries which you get from to make a battery pack, or else you can use those battery packs into a complete vehicle. So this is the one problem and the context which we are going to address in this case. So we will be beginning. We will be talking about the COMSOL multiphysics, and then we will be talking about the tool which can help you in this case, and then different approaches which will be available to model the battery or battery pack for you. So there can be 4 or 5 scenarios which you can deal with. First will be performance side. So performance will be where you are having a battery, and then for different kind of operating conditions like temperature, SOCs, accelerations, ranges. If you want to deploy that battery pack into a vehicle, then how that battery is performing. So that will be performance at the local basis. But in some cases, when you use that battery for a long period of time, or else due to the from the government norms, you should know exactly that how much capacity you are holding with you, and then with time how you are losing your capacity, because you will manufacture a vehicle and then that will go to the extreme hot environment, to the extreme cold environment, and then you want to provide the warranty to the both customers who is using in cold environment and to who is using in a hot environment. So these kind of problems you can deal with when it comes to the capacity or the range anxiety. So when you have a range, you want to provide the proper range to you want to provide a range or warranty to your customer that it will run for 200 kilometers, 500 kilometers. And now there is a competition between the people that who can get a vehicle which can run very for a longer distance. At the same time, the performance should be very optimal. So the temperature should not rise much, and then you should be able to draw as much power as you want. So there will be one range which is capacity, and there will be power which can contradict to each other because of the design problems. So these problems, if you are dealing with, then we can talk about those problems here, and then we can see how we can work with those problems. And then ultimately, if you are working on on any system, then you want to have to ensure the safety of that particular scenario. So then you can know, you may get the failures of those battery and battery pack, and then we saw some cases where vehicle itself is getting burned off. So we can investigate the cause of that failure, and later, if you want to mitigate those kind of failures, then how you can do that. And in worst case, when you can't mitigate or you can't do anything about it, then what measure should we have to at least have a safe operation? And then if it is failing, then how we can detect and know the why battery is failing, and then can we replicate that failure behavior in any virtual background and virtual platform. So then we can avoid testings, multiple testing and burning of our real batteries. And then finally, if you have answers for all of them, then you want to have to satisfy or convince the approval authorities that okay, this particular vehicle is having very good performance, very good range, and it don't fail in the real operating conditions. So all those scenarios we can talk about. So now there really was one poll that I just want to launch. That I want to know that are you using any simulation tool, or using COMSOL, or you want to uh, you are attending just for their personal interest. So then what kind of so what you are doing right now in modeling, and what do you expect from this session? So I request team to launch this poll so then we can get the response. I hope you all can see the poll in front of you, to where we just want to, are you a console, are you a regular simulation user, or else you are new to multi-phase simulations, or else you are attending for your personal interest, or else you are evaluating the simulation tools for your any ongoing or upcoming projects.
Yes, sir, the poll has been launched. We are receiving votes. So
Yep,
I'll
yep.
keep the poll on. I'll hide it from the stage for the time being, but I'll keep it still launched.
Okay, fine. Thank you. So yeah, so as we was discussing, that we will be addressing those queries. So first we can introduce you quickly that the tool which we're talking about, the COMSOL multiphysics, how it can help you, and then how it looks like, that what kind of capabilities are there available to fulfill your requirements. Let's say you starting with a project where you are at a stage where you are in a modeling stage, and then there will be team which can be involved in that. So then how all those stages, how that particular tool can help you. So just to start with, this is one COMSOL GUI, COMSOL multiphysics suite, where we can see you will have one platform called COMSOL multiphysics, and then there will be different other physics which can help you to design the different aspect of your e-mobility components. So here we can see we can talk about battery design module, we can talk about fuel cells, we can add the CFD and heat transfer to it to get one better model. In some cases, you may see your structural mechanics also play an important role. So your structural mechanics also will be there. You may be interested to know any kind of RF or AC/DC electromagnetic components. So those also will be there, and then you can couple it with different tools like MATLAB, Simulink, or the other CAD tools. So that way, now you can see if any problem which you have, which is in multi-phase in nature, and if you talk about battery specifically, so it involves the features from the battery side. It may require the features from the chemical reasoning side. It may require the feature from the corrosion side. So this corrosion is a very area where which is people generally neglect. So let's say you have battery which is connected to a terminal. Now the terminal and the battery are both are metal, and then it's exposed to the humidity. So then you will see with the time you will form a galvanic pair, and then with that galvanic pair will give you some kind of contact resistance. And then because of that local heating, you may see the local failures may occur. So you may have the corrosion modeling, you may have the heat transfer, CFD modeling. When you are want to design flow fields for your cooling channels, then there can be pipe flow. There will be different kind of structural aspect, let's say external load, impact, or internal stressing due to charge discharge cycling. So all those features will be there. And then ultimately, when you want to optimize and you want to quantify your uncertainty which can be occur during your operations, so then all those things can be covered in this case. So now, if you think of any scenario and you can post your queries and the things which you want to know, uh, which may be in multi-phase nature or for the fundamental side, so then we can discuss those things in detail in the Q&A question and session. For now, we will just going through the introduction for the COMSOL and then we'll see the battery design module. So here, let's say if you want to work on any problem, which is in nature, it is single physics as we discussed in battery. That you can just focus on the heat transfer, you can focus on the fluid flow, you can just focus on the electrochemical reactions, you can focus on the structural part of it. So that the problem can be in single physics. But in other case where you have the problem which is multiphysics in nature, and then you want to solve all those physics and coupled behavior all together, then there will be multiphysics scenario that we can solve for. So now to do that, what we can have this environment GUI, the COMSOL GUI, where all required things for to the modeling will be available. So let's say you want to make one geometry, you want to assign the materials to it, you want to assign the different physics, and then you want to couple all these three physics by using this multi-physics node. And there can be multiple analysis which you may be interested to know. So then there will be different analysis which can be done by the same interface. And then ultimately you can post process and see and draw some conclusions that what you got after those analysis. So post processing also will be available in single GUI. So, and then you can see things in details, like let's say we will take one battery example. So, to make a model, what you need first, you need one geometry first. So then you will take the geometry, and then that geometry can be imported one. That geometry can come from your any CAD tool, or else you are creating a parameterized geometry here itself. So then you can create that geometry, and then the next thing, the geometry can be parameterized. Here you will be having all those operations, let's say extrude, work planes, and then so one complete parameterized geometry can be created here. The next thing which you may want, that we want to identify which domain is built of what material. So then there will be one battery material, air which is surrounding the battery. You have aluminum for bus bars, you have copper for bus bars, and then you have active material which is for battery. So we know that okay, how my battery will look like, a battery pack will look like, what components will be there, and then what material they will be made of. So we'll have the geometry and material defined to that, and then those materials may have different properties which may be required, but or which may not require. So then all material property will be listed, and then the required material properties will be highlighted in this case. And next, then now you want to know how that will function. So that means we want to know which physical phenomena will govern this particular device. So in this case, we know that the batteries which you want to analyze, we want to use the battery physics, and then those that battery physics can be detailed one. Here in this case, let's you can visualize and see which equations you are solving. So when you know that which equations you are solving, then you will be confident enough that whatever you are solving is good enough, or else you want some modification in that, and then you want to correct them. So in that case, corrections also will be available for you. So it's not a black box which is you are solving, and then you can get confident about the physics which is running in background. You may see, let's say in some cases, the other physics also comes in picture. Now here we want to add heat transfer to it. So this is one general form of heat transfer which we are going to solve. And now your battery material may require specific space dimension, material properties. So if you have, so when you see a jelly roll, so through the plane or through the layers and across the layers, along the layers, there will be different conductivities you will experience. So in that case, if you will be able to assign the properties in the case where they are non-isotropic in nature, then that will help you more to get more near to more reality. So those kind of specific features you can see to design those kind of batteries. And then ultimately you want to couple them and you want to solve them. So then this inbuilt multi-phase feature is available here. And then you can solve it, and you can create a mesh, and then you can solve it, and then ultimately you want to know the results out of it. So then there will be temperatures and the the SOCs, voltage, and then the other plots will be available. And you can see the any kind of experimental data which you have, so you want to validate also, so then both can be plotted together. So now in this journey, what we saw that it will be very easy for you to work on this particular tool because the physics is available to you, the equation which you are solving is available to you, and then they are getting solved automatically. You don't have to change GUIs multiple times, and then it will be easier and convenient for you. So that way, you can do your entire modeling study. So now you are one modeling engineer where who knows things in detail. So then you are a modeling engineer or the app designer. So you can create a model in detail, and then that model having all required details, and it is completely editable model which you have, and you can create models for different scenarios. But let's say you want to collaborate with your team, and the teams may come from the different other backgrounds like mechanical, electrical. They can be from non-technical background like sales. They can be from marketing. They can be from the different other departments. So then, what you can have, you can create simplified GUIs, which we call applications. So then, the app can be created by using those models, and then the real model which you have built will be running in background. So that way a different GUI will not require much competency and much knowledge to solve that model, but the other team can just put some inputs, and then they can visualize the results which they want. So you can create one customized GUIs for different teams for same model. So let's say you want to create a model for your design team. There you just want them to change geometry, and then they will change the geometry and then analyze the different designs with that. You want to make a model or that app for your sales team, so then they will go in field and demonstrate, okay, how your models and batteries are behaving for the different conditions. So then that sales team will take that app, which is very simple GUI. They can put that number and then run the model in front of their clients and customer, etc. So it is not necessarily to have that technical competency to work with those kind of applications, and that apps can be designed very detailed, very simplified, and for different aspect and different kind of people. So collaboration is one key which is you can make a sure. Other things which will be available here that the app having one mask with that, so that means the UI is different. So then whatever details you have feed there, then those will not be available or visible to any other people. So this gives you one complete environment, and then that can go up to field technician, where you can see those field technicians also can work with those kind of apps. So now, as in whole, as in company or as in project, you can work with different people, and then the same model and same GUI, same compute tool can be utilized for different stages. And then we can host this entire research or the entire project into a model manager, where you can do the version control. You can provide different kind of filters. You can efficiently store your models, and you can provide the specific access to the specific people. So then you can control your research and do maintain or ensure your privacy as well. So this is one brief introduction that how you can deploy this tool for different aspect and different areas. Now I just want one more information from the audience that, okay, which problems do you face in battery analysis? Is it the range which you are talking about? Is it really risk analysis, risk and assessments, or lack of material property data? You don't have material property and you want to do a modeling part. You want optimum performance assessment, or you want to use or you want help in the certification from the approval authorities. So I request team to launch this poll so we get responses, and then we will talk about for specific topics.
Yes, the poll has
Yeah.
been launched. I have screened it on the stage.
Thank you. Yeah, so while you're providing responses, we can talk about the things which we are going to talk about. So we will be quickly seeing that, okay, what all you can do when it comes to very specific about battery modeling in this case. So I hope we you can see presentation now.
Yes, sir.
Okay, thank you. So, what we'll do, we will see how we can utilize this tool for your applications. So, when we talk about battery, first things comes in everybody's minds will be lithium ion, but it is not necessarily that you are working on lithium ion. You may work on the lead acid batteries, which are the conventional batteries, which are being used now as well for the auxiliary power in the bigger vehicles, smaller vehicles, and they are a bit cheaper also. So you may be working on the lead acid batteries. You may be working on the future technologies where those are the sodium ion batteries or flow batteries for the large scale energy storage, or else you are working on a current trend which is lithium ion battery. So when we talk about battery modeling, it is not only about lithium ion; it can be anything in the domain. So, if you wish to work on any kind of battery, so all major battery chemistries can be modeled. And why it is possible? Because you are working with the Nernst-Planck theory, and Nernst-Planck equation can handle any kind of electrochemical setup. Only the mode of mass transport, materials may be different, but the physics will remain same to drive those kind of particular setup. So we have Nernst-Planck equation to solve for them, and then there will be different chemistries, different components like porous electrode, solid electrode will be taking part in that kind of reactions. So we have Nernst-Planck equation which can handle only all kind of battery chemistry. And once you know your setup, then you want to do the analysis. So that analysis can be transient, that analysis can be impedance plots, because when you see most of the published articles from the academicians, they are coming from the impedance side. So they publish the impedance data and they reported their electrode or cell behaving in a certain way. So those kind of impedance plots, if you will be able to generate, so then you can compare your models, your particular setup with them, and then you can verify that whatever you're doing without performing those experiments which they perform. So then you will get same models, and then you can do the analysis part. When it comes to the industrial side, then you may see lots of transient data available. So you have the range data, you have the charge cycling data, you have the any kind of random drive cycles which is available to you. And then if you will produce those transient data, then that will help you to again build a model and modify your model again, and if it is not meeting your requirement. And then if you want to go more realistic, then you want multiphysics as we discussed throughout the session. So you can add the heat transfer, you can add the friction mechanics, you can add the fluid flow to fulfill the different aspect of it. Now, you may ask that, okay, let's say I am a mechanical engineer, or I am working from only for the battery pack, I didn't get the material property, or else you may from the fundamental side where you are having a material property, you want to build a model, and then you can take up that material model till the pack modeling and the performance side. So then there can be multiple kind of problems or different kind of users which are possible in the domain. So how that particular problem can be handled. So let's say you have material property available with you. So then you may make one detailed model, which are the electrochemical models based on the Newman's theory. So you are having Newman's model where we have 1D, 2D, 3D models with one extra dimension, and generally people call them when they have 1D with extra dimension, it will be P2D models. So those P2D models can be created, and then those P2D models can come from, and then they can from the various kind of chemistries, and then you want to analyze for design, performance, aging, and the risk scenario. So there will be P2D models, but someone wants to deep dive furthermore, and then they want to make a electrode level model. Then you can create one heterogeneous models where specific particles also will be visible to you, because you can see the specific particle information, particle of distribution, their phase fractions, and then the path which is involves toxicity, and all those scenarios also will be available. So then we have heterogeneous approach as well. In some cases, when you want faster results with electrochemical models, and then you want to use them for parameter estimation or onboard applications, or else you want to make a battery pack where you may require hundreds and thousands of batteries model to run at the same time. So then they can have a single particle model. So the material properties available to you, and you will be able to model the different aspect of batteries. And then the same battery models will get extended for the battery packs. Here you can see we can extend the homogeneous models and single particle models for the battery pack design. Now let's talk about the people who don't have material property, what they will do. So generally they are doing the circuit modeling. they're representing or they're making their batteries as in circuit the circuit components. So they have 1 RC, 2 RC kind of scenarios, and then they are making this battery models. But you may struggle to make those kind of circuit modeling when the complexity increases. Let's say there is a degradation, let's say there are different temperature conditions, let's say there are different other SOC conditions are available, then what will happen in this case? So then you may require one approach which should fulfill all your requirements. Then you can move towards this lump model, which may not require or which will not require the material property data, but some test data, which is your drive cycle, discharge curve, impedance plots will be required, and then you can make one battery model. And then the same battery model get extended for the pack modeling, and then you can individually monitor your individual cells in the pack and with their locations based on their temperature, physical connections, and analyze your pack as well. So now we can see two different groups who works on fundamentals batteries, and then they have material property. One person who want to make a battery pack, or else they don't have any let's say any kind of permissions to tear down the battery because of NDA issues. Then also you can utilize these tools. So that way, the various problems and various kind of group of people can utilize this tool for their applications. Now we talk about different kind of people. Now different scales also matter. So let's say you are at micron scale or a pack scale, or else you are starting from micron scale and you want to go up to pack scale. So then that entire range also will be available. So then you can model those different kind of scales in this case. So and then there will be full electrochemical model, and then you can do the thermal modeling in this case. So now we know how we can model one battery with our available data, and then based on our background, then level of complexity which we want. So then there can be different kind of studies which are possible. So study wise, you will have the transient study, and then you can have the impedance plots, and then you can utilize them for the parameter estimation. So these are the typical studies which we discussed earlier also, that they can be utilized to validate your model, to do the parameter estimation, or else you want to analyze for parametric sweep, so to know the performance at different operating conditions. So let's just see one simple model, which is 2D axisymmetric model. What will happen? When we see one cylindrical cell from the top, so then you can see this top view where all layers are in spirally wounded, and then you have a jelly roll. So then you can create one a full 2D model with intercalation. So then there will be a 2D model with one extra dimension, so it will be P3D model. So then we can P2D model, P3D model, and P4D models can be created. So now what we can see the positive electrodes in the inner coil outmatched with positive electrode in the outer coil. So these internal differences, if you are interested, then we can utilize it, and then you can see how that will perform. And then again, internal coil of the positive electrode and the outer coil of a negative electrode poorly utilized, so do not contribute to the battery capacity. So you have stuffed your material inside, but it is not helping you. So then, if you are at a level where you are making a battery, then this kind of 2D analysis can help you to do this analysis. Now you may get interested to know, okay, what if I want to make a 3D model. So then let's say you can make a 3D model. But what happens when you go by jelly roll or the pouch cells? So then we just want to know that should I be at 1D level, or should I go to 3D level? So it is possible you can create one 3D model. But what will happen when you see the comparison of your 1D model and 3D model? Then there will be only 2% deviation. So then wherever it's required, you can utilize the 1D model for as an heat source, as a performance indicator, and 3D models may not be required. But if it is required in some cases, let's say you want to design different tab condition, you want to do different tab location, you want to try different material, you want to do any kind of modification in geometry. Let's say you may have a jelly roll, you have a stacked prismatic cell. Uh, there can various kind of analysis, and the ideas are being implemented right nowadays in the batteries. Then you can try those 3D setups also. Now this is all about the battery specifically, but now the people who want to make a battery pack, then for them I can create a battery pack out of it, which will be you are having systems and model to be built. In this case, again, now we can extend those lump models and then want to make a we can get a 3D thermal management model. So now you just have a 0D lump model, add heat 3D heat transfer, and create one battery pack model with that. So, but why it is required? Why to maintain or get a temperature or thermal management? So then there will be various scenarios that will be possible. So then you can see the cooling. You have accelerated degradation like acid formation, gassing at higher temperature. So when you cool it down, the optimum temperature which you want to maintain, which will be 30 or to let's say 25 to 45 degrees Celsius. So then that will slow down your deterioration. So you want to cool down the battery to slow down your degradation mechanisms. What will happen? Let's say you have a battery pack, and then there is a hotspot identification. So you design your battery pack for uniform temperature or one temperature gradient, but then suddenly you figure out there are hotspot, and that hotspot again can lead to the accelerated aging, and that may give you a risk of thermal runaway as well. So that local point is pretty dangerous. So if you want to identify for your design, do we have any hotspot? Then we can do the one coupled analysis for thermal management and do the hotspot identification. You are selling a vehicle or making a vehicle for cold environment also. There again, you want to maintain the temperature of 25 degrees Celsius. So all these things I am talking about in context of lithium and battery. So lithium-ion battery required from 35 to 45 degrees Celsius. So then we want to heat up the battery to when we start up or work with at low temperature conditions. And then when we don't do it, then there will be low performance, and then lithium plating will also be more dominant. So there's a case where you want to start up from the cold environment, or else you want to operate at cold environment. So then you want to know how much heating should you provide externally and how much heat battery will produce itself to maintain the temperature. So then that kind of operation where you have a low temperature of operating condition, so that also be available. And then in worst case, it can fail, and then you want to know the thermal behavior of the batteries, so then you can analyze those battery packs. So what mode of heat transfer will be available? So generally there is conduction, which is taking care everywhere. In the battery, you will see there all are solids. Even the gas is filled in that, or the fissile material are filled in that. It is conduction only. So first thing which you want to solve is conduction, and then later you want to solve the advection if you are having one active cooling. You are having air cooling, you are having immersed cooling, you are having any kind of cooling channels. So then advection also can be solved at the same time where laminar flow or turbulent flow, where you can deploy fans, you can deploy any kind of cooling channels. So those scenarios also available in case of advection. So conduction advection is sufficient enough to analyze one battery and battery pack, but you may see one scenario where you parked a vehicle at open environment, and then sun rays coming on that particular vehicle, and then because of sun rays your battery is getting heat up. So if you want to know that where to place the battery in the vehicle, when you want to know whether radiations will affect your battery, because you can place your battery very near to some other component, and that may radiate the heat. Let's say your radiator which is cooling down the battery, that may radiate the heat. So then the location and the orientation because of radiations also will be important. So surface to surface radiation and surface to ambient radiation where it is cooling down, and then ambient to surface radiations also may play a role when you want to test it for those conditions. So then you can integrate all these three and then see how your battery will perform in conduction, advection, and radiation case. So we know why to do the thermal management, and now we know which kind of approaches we can deploy, including battery modeling. So what will couple both of them? Your heat transfer and battery will get coupled by using these heat sources. So the heat sources where we can see they can become from joule heating, electrochemical reactions, bit of mixing. So if you will be able to plot them specifically, so what you are obtaining in this case, you are having the different components which may give you that heat source. So you have the joule heating that will be coming from the conduction parts, which ions and the conductors. You can work on those materials if it is in your control. If there is a chemical reaction, so then if it is any kind of catalysis which you can work on, or else you can want to limit your operations for certain C rates, certain loading conditions, and then you want to give the warning for your user that okay, don't go beyond this speed, don't go beyond the C rate. So then those kind of electrochemical reactions or joule heating scenarios can be calculated, and then you can give the exact warning when you want to uh, provide one manual to your user. So then you now you know that at what heat source is available, and you are plotting them individually. So then you are making sure that okay, you are talking about the right things in this case. So let's just take one example. So what will happen? Let's see, we have one huge stack. So we talked about enough that the individual cells and the battery. Now we'll talk about one huge stack. So this huge stack having four lines, and for each line with there's a 14 cells, and there is a 8 modules are available. So what this gives you a very huge stack which is having 300 million per hour per line, and then you can generate 360 volt out of it. So one huge jumbo stack is available to you. So to pull it down, then you may require the thermal management system. So then there will be plates are available, and then in that plate we will have the coolant flow. So then there will be flow in vertical pipes, flow in horizontal channels, and then you will see the one coolant is being used to do that. So now let's say if you want to make a battery pack model, then you are focusing on voltage loss, you are focusing on the capacity loss, and thus in this case you are seeing those equations which are being solved there. So one detailed model is available to you which is giving you heat sources, and then if you are running it for the, let's say, 6 months, 1 year, then what will be the variation in the heat sources, because they may differ from first cycle to last cycle. So then you bought a vehicle, so initially it was not heating up much. Now after 1 year you see that heat generation is more. So then you have to deploy more coolant, and then that will eat up your battery more, and then again you are losing your capacity. So that cascading effect will be there, and then again ranges may get decreased. So you can solve voltage loss and capacity loss at the same time, and then both will affect each other, and ultimately you can couple them by heat transfer, and then you can generate the results like this, where we are seeing the temperatures. We can see the what is the electrochemical profiling, what is the maximum temperature, and what flow rate you need to do provide for optimum cooling. So now we can identify the hotspots. We can identify what is will be the flow rate, how battery is performing for that particular condition, and then we are monitoring the maximum temperature. So which covers your all three concerns, where performance, risk scenario, and as well as capacity are being considered here. So now let's say we'll see one example. So how that will be built in COMSOL, we can see that. So we can open one COMSOL interface, and then same model can be used. So this is the GUI which we talked about, and now here we have one that geometry which we want to work with, and that geometry, this particular geometry, let's just uh, hide this. So then this particular huge stack is available, and then here we are deploying the turbulent flow, pipe flow in the channels. We have the heat transfer in solid fluid, heat transfer in pipes, and then there will be battery pack. And the same details which you saw in the presentation will be available for the batteries, which is your voltage loss and capacity loss. So this scenario will be available to you, and then we can analyze the heat sources, we can analyze the velocities, and then see that particular stack in detail. And then if there is an analysis wise, you can play with different analysis can be stationary, time dependent, and then you can see the meshing also being done here itself. So this is how we can analyze one battery pack in detail. So now let's see what other details may require to model there. So now there will be thermal runaway and aging, which can concern you. So aging wise, there will be plating, short circuit, gas evolution, loss of electrolyte, acid formations. All those degradation phenomena are available. But and if you know, you can model that. But in case where you are not aware of these phenomena, and the material property and relevant data is not also supplied to you, in that case you just focus on the operating conditions like current, temperature, aging history, and we can see the capacity loss calculations. And in worst case, when there is a thermal runaway, it can be because of internal short, external short, then that also can be tackled in this case. And we can see the propagation. So we will see one example where we can animate that thing as also. So let's say there's a one cell which can trigger, which can have all these details, and then you want to analyze it. There will be exothermic reactions which you want to model, and then ultimately you will see at what temperature, at what condition your cell is getting fit. You can extend it for the pack level where there is a pack simulations, and then you can see the failure because of let's say due to only conduction, only due to, because of gas venting, and because of any kind of combustion reactions. So it can be combination of anything where the propagation is happening due to the conduction, gas venting, or else due to combustion reactions. And then, so let's say if you want to model that, how we can model, we will have again the same interface called battery pack, and then we can trigger those thermal events. So thermal events can be due to the any temperature or a specific condition. So we deploy them and we can do the thermal runaway propagation test. So let's say we want to do the thermal runaway propagation test, and then what kind of results we will obtain? We can obtain this animation where we will know how the propagation is happening in this case. So we have this propagation animation available. We can see the voltages, and because of voltage also we can see how failures are happening. So let's see temperature and voltage at the same time. So when we see temperature, there is a it's getting failed, and then we can see one certain T max is suit up, but average temperature is getting decreased. And then there will be subsequent failure, and then those failures will give you the T max rise, and then T average also rise, and then you can see ultimately battery will die off, and the temperature will start reducing in this case. And similar thing can be observed by using SOCs. So then you can see one completely discharged cell also will be available to you. So this is how we can do the thermal runaway assessment. And then when we know there is a thermal runaway, so what we can do about it? So there was a previous thing which was available to you where we saw that there is a liquid cooling is available, and then you can deploy the phase change material also. So that phase change material can be deployed easily in the heat transfer, and because of we can compare because of air convection and phase change heat transfer, what will be the performance change in this case. And then you can add different degradation mechanisms which is at different forms, and individually you can monitor those in detail, and ultimately when they will come all together, then we can see the loss in capacity in terms of storing. So you can make a battery pack and you store it, and then after 1 year you will see that you lost some capacity. So at what condition we should restore the battery, at what condition we should use the battery to get your optimum performance, or else the reverse case where you did or used it at a certain condition or stored at a particular condition, then what was the outcome of that? So there can be calendar easing and the cyclic aging. So those also can be performed in this case. So just to conclude that, okay, now we can use the battery design module for various applications by it can be used for various level of competency with various people, and then we can utilize it very well for different applications. So now, before just starting the Q&A, I just want to inform you that we are having one COMSOL day. If you wish to meet the COMSOL team, then that it will be available on 27th June in the Chennai. So if you are around the Chennai, then you can meet our team on the 27th June, and you can register to our this COMSOL day, and then the further details will be conveyed to you. And before start, so now we can take a question. At the same time we can just launch this poll where I just want to know that what you will be doing or what you will be interested to doing after this session. So we can launch this poll, and at the same time we can start having the questions from the audience. So let me go to the uh, forum where we can see the question. So now, as I can see, there are multiple questions has been posted at the different time. So let's see what questions we have. So there's a question that will you be sharing the presentation deck? I think I'm not sure. I have to check with my team. There's a question that what are the latest innovation in the field of battery design. So it is a very generic question. So where if you want to wish to know that what are the innovation has being done, so then people are working with different kind of materials. So people are going towards now silicon battery where it is giving you more bigger like larger capacity and the larger, but at the same time they are giving you some kind of drawbacks like mechanical degradation. So people are working on different kind of materials. People are working on different kind of flow, different kind of cooling mechanisms, and different kind of battery pack design as well. So innovation wise, it can be from the material side, from the performance, from the design side, or else it can be from the fundamentals. Let's say electrode modeling or the pack modeling. And then there's one follow-up question for the same. What type of simulation studies are done and which are leading expert to conduct studies? So these different kind of so we can have the different simulations as we discussed. So it will be for the performance analysis for including thermal management, structural mechanics, or else it can be from the capacity loss. So capacity loss analysis also can be done, and we can see the different analysis which will be from the risk scenario. So all those scenarios are being uh, scenario being modeled, and we can perform the simulations for that. So it depends on the person to person, and we can but and then we can see uh, what area they can work on. So let's just see some other question. Yeah, so there's a question that from where could we get the thermal conductivity and specific heat of battery? Any resource, please specify. So just to mention that COMSOL also have one material library where you can go and get all this information for all state of art material. If you wish to know that, then you can contact us. Otherwise, it will be available in the literature. So that one specific because it's a very proprietary data for one of the manufacturers, so they generally don't publish it. So it is very rare to get in found from the manufacturer, but they can be available from the academicians, and then they are reported in published literature articles. And if it is not available and not reported, then you can and you have the performance analysis, so then you can utilize COMSOL also to obtain those material properties for you. Uh, there's one more question that which type of battery is most suitable for the rooftop solar application. So I think it depends on your uh, requirements. So let's say if you have a rooftop solar applications, but so you want to use these batteries for the large scale storage, then in this case, I think lithium ion will be much more costlier for store that standalone applications. In that case, you can take help of these lead acid batteries, or else the flow batteries are now on the coming trends, which can be utilized for those rooftop applications. Yeah. Yeah, one final question that can we add BMS in the simulation in COMSOL? So yes, you can add the BMS also. So for BMS, so let's say you have battery back model and then you make an app, and if you have if one chip is available to you, then you can use a model to test your chip. Or else if you want to generate the data for your BMS, then that can be generated with COMSOL, and you can work with Simulink where you can design those control scenarios. So you can add the BMS with the COMSOL simulation in terms of app, and then you can test your BMS set scenario. So which is being done one of our customer where they have the BMS available, and then the battery models are being used to test those BMS in this case. And then APIs are available with Java, Python, and the Simulink MATLAB. So it is very easy to integrate with your BMS also. Uh, so do we have more questions?
So that's it for the
Okay.
questions. Okay. Thank you very much, Dr. Ustam, for that very interesting and insightful presentation. I'm sure our audience has taken some great takeaways from your presentation.
Thank
So
you.
thank you to the audience as well and for your questions. With this, we have come to the end of the webinar. Again, I would like to give a big shout out to our attendees for extending their time and support for the event, and a special thanks to our partner COMSOL for extending their immense support to organize this event. We promise to be back soon with another exciting session. The floor is now open for networking. Thank you all.
Thank you.